Deformable medical image registration, a crucial step in medical image analysis, has seen the application of transformers, which outperform convolutional neural networks, CNNs, but are limited by high computation and memory loads, restricting their ability to capture fine-grained long-range dependence at full image resolution. To address this limitation, multi-layer perceptrons, MLPs, without self-attention have been explored as an efficient alternative, enabling the capture of fine-grained long-range dependence at full resolution. This study proposes the first correlation-aware MLP-based registration network, CorrMLP, for deformable medical image registration, introducing a correlation-aware multi-window MLP block in a novel coarse-to-fine registration architecture. The CorrMLP leverages MLPs to model long-range dependence, addressing the limitations of transformers, and captures correlation-aware multi-range dependence via multi-window MLP operations. The correlation-aware multi-window MLP block calculates local correlations between feature maps and captures correlation-aware multi-range dependence, enabling the CorrMLP to perform correlation-aware coarse-to-fine registration. The CorrMLP architecture consists of a hierarchical feature extraction encoder and a correlation-aware coarse-to-fine registration decoder. The encoder extracts multi-scale hierarchical features from the moving and fixed images separately, producing two 4-level hierarchical feature pyramids. The decoder leverages these feature pyramids to perform 4 steps of coarse-to-fine registration using correlation-aware multi-window MLP blocks. The CMW-MLP block takes 2 sets of feature maps as input, explores their potential correspondence, and captures correlation-aware multi-range dependence for deformable medical image registration. Each CMW-MLP block has a 3D correlation layer to calculate local correlations, followed by a multi-window MLP module to capture multi-range dependence. The resultant features are fed into a deformable registration head to map the features into a displacement field. The CorrMLP model is a novel MLP-based coarse-to-fine registration network designed for deformable medical image registration. It leverages a correlation-aware multi-window multi-layer perceptron (CMW-MLP) block, which captures long-range dependencies in a hierarchical manner, and integrates it into a novel coarse-to-fine registration architecture that considers both image-level and step-level correlations. The model is optimized using an unsupervised loss function comprising an image similarity term and a regularization term, encouraging smooth and physically realistic spatial transformations. The CorrMLP model outperforms state-of-the-art registration methods in both brain and cardiac image registration tasks, demonstrating the effectiveness of MLPs in capturing long-range dependencies crucial for precise dense correspondence. Quantitative comparisons on the Mindboggle and Buckner datasets, as well as the ACDC dataset, show that the CorrMLP achieves higher DSCs and lower NJDs than other state-of-the-art methods. A qualitative comparison illustrates the superior registration results produced by the CorrMLP, with cleaner error maps indicating better alignment with the fixed image. An ablation study on architecture designs reveals that both image-level and step-level correlations are beneficial for coarse-to-fine registration, as removing either type of correlation information degrades the registration performance. The effectiveness of the CMW-MLP block is validated through an ablation study on MLP blocks, where replacing the CMW-MLP block with other existing MLP blocks results in lower DSCs. The study also demonstrates that the multi-window design of the CMW-MLP block is crucial for capturing large and subtle deformations in images. This comprehensive review of deep learning techniques for unsupervised deformable medical image registration focuses on transformer-based models and their applications. Image registration is crucial for analyzing anatomical changes over time or comparing images from different modalities. A comparison between convolutional neural networks, CNNs, and transformers highlights their respective strengths and limitations, with transformers showing promise in capturing long-range dependencies. Transformer architectures, including hierarchical vision transformers and pyramid vision transformers, have demonstrated superior performance in various tasks. Self-attention mechanisms in transformers model complex spatial relationships and long-range dependencies effectively. Multiscale features are essential for capturing both local and global information in image registration, with pyramid networks and multiscale transformers leveraging this concept to improve registration accuracy. Dual-stream networks, utilizing both image intensities and spatial coordinates as inputs, enhance registration performance. Non-iterative coarse-to-fine registration networks reduce computational costs while maintaining accuracy. Applications in cardiac and brain imaging require accurate registration to analyze anatomical changes over time, presenting challenges such as dealing with large deformations and ensuring topological preservation. The paper discusses future directions, including the development of more efficient and accurate transformer models, and the need for large-scale datasets and benchmarks to evaluate these models effectively. The authors emphasize the importance of addressing these challenges to advance the field of unsupervised deformable medical image registration. The review highlights the potential of transformer-based models in this field and provides a foundation for future research.